Well, hello and welcome YouTube. Mr. Robbins back here with yet another brand new exciting video, all math basic course. And as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Step one inside as we explore section 1.3 in the Big Ideas Math Integrated Math 3 textbook on cross sections of solids. Now, this is one where things might go a little poorly, all depending on your perception and my perception combined. See, I have to provide good artistry, and you have to be able to see three-dimensional aspects in 2D, but literally actually even see two-dimensional aspects in 2D cut from a 3D object. So thankfully, you know, as I formatted stuff out of the PDF here to make it right, by the way, you can download this PDF down below. You know, I see some visuals from the book that look promising. They look like things that, at least I can always make sense of these things. I don't know if you can as well. A cross-section is way is cutting through something, like I say, slicing through meat, a block of cheese, something like that, and just what shows up in the two-dimensional surface. So let's take a look at this, see how it goes. Take a look at the lecture portion to begin with. This is where you might benefit most from it, because my guidance can be through their visuals, and then I'm only going to do the best I can through my own drawings from this stuff. There are 26 problems in total. Let's see how they pan out to be. We are going to describe and draw cross sections and solve real-life problems involving them. Cross-section being the new phrasing here. Plane is something you're going to have to know. You know, a plane is anything that's a two-dimensional kind of surface thing. It could be, you know, like these orange, if I call them orange, salmon-colored things are planes right now when a plane cuts through it. And then using Pythagorean theorem, I suppose, and square roots. I don't know where that's going to be used just yet. I assume with some of these lengths here. So, okay, describing cross sections. Let's take a look and see what they say, see what I can interpret for you. Imagine a plane slicing through a solid. So here's your cube, if you will, and the plane is the salmon. I'll call it orange, the orange-colored thing. The intersection of the plane and the solid is called a cross section. For example, 3 different cross sections of a cube are shown below. So in purple is the cross section of the plane intersecting with the cube. Imagine that you had a square and a line going through it. The cross section of the square and the line is everything from here to here, right? That's in two-dimensional stuff and getting a one-dimensional cross section. Here is three-dimensional items, or well, one's two-dimensional, but in three-dimensional space, cutting through a three-dimensional item and making a two-dimensional cross section. This plane, this square that's cut out. And you might say, that's a parallelogram, that's a rhombus. You have to imagine it in 3D space. It's a cube. We cut through it, and this is the part where you're going to have to do best. I have a Rubik's Cube right here, 2x2. But imagine that you cut through it in some way that you only see that white facing now, right? So that is what's happening there. You can also cut through it, say, diagonally, and out comes a rectangle, as long as you have opposite sides congruent, as long as you have all right angles, that kind of thing. And that seems to be happening when the plane cuts through the corners diagonally. And then you could also make a triangle if you cut in and out of such corners in such a way, look at the purple alone, that, you know, that happens, right? But it's where the plane intersects the solid, and that's where I'm going to have to do my best with my own drawings. I haven't practiced it. I can't imagine this will look great. So again, their visuals are going to have to be best for you from me. Describe the shape formed by the intersection of the plane and the solid. So this first one, this plane is intersecting vertically with this hexagonal prism, and out comes a hexagon. That's the cross-section in purple. Cross-section's a hexagon. Part B, you have some triangular pyramid, and this is cutting horizontally through it. Out comes a triangle. I don't know what kind. They just called it a triangle right here. Part C, you have a cylinder cut vertically through this, and, you know, it depends on how you cut through it. This is vertically through. And there's nothing circular in the cross-section. It's just a rectangle. You can see there. So I got to sneeze. Excuse me. So all you have there is a rectangle. Next one, you have a cone cut horizontally through, and you have the circular cross section because it's a cone that's circular parallel to that. That's a circle. Part D. Part E, you have a sphere cut vertically through. That sphere is going to be a circle in and of itself, the great circle. That's what you call the circumference of the item. And then part F, what's that? I guess a trapezoid. It's cutting kind of diagonally through the cube, but in such a way that it still exits out the bottom. It enters through the top, and it exits out the bottom in such a way that you have different sized lengths here, but parallel to each other. So it'll make a trapezoid, and that's what they're calling that one, trapezoid. Okay, let's move forward. Drawing cross sections. The plane intersection postulate states if two planes intersect, then their intersection is a line. Okay, yeah, like these two right here. You intersect this plane with this plane, you get a line. The postulate can help you when drawing a cross section. Draw the cross-section formed by the line parallel to the base that intersects the red line segment drawn in the square pyramid. What is the shape of the cross-section? So they're saying make sure that your plane is parallel to this guy. I should practice doing one of these drawings here. I know I got to do them later, but I haven't done them yet. I don't know what kinds of colors I should use. I'll start with blue and see where I go from there. So we're parallel to this thing, right? Plane cutting through it. But then, you know, we're staying parallel to that as we come the other side. Should I go? I guess I'll go like that when I make it happen. And then I'll try and do, I don't know. I got to figure out, I literally got to figure out how I'm going to make this thing work best. I'll try and do this kind of a transparent look here like that. But that's not the cross-section in and of itself, right? What cuts through it is, oh, this is going to be very hard to do, guys. This is going to be fun. So dotted line. What the cross-section, though, is this guy right here, right? So I don't know if that works. Maybe I can fill it in or something like that. But that's going to be a square if it's a square pyramid. It is a square pyramid. So that's what it cuts through. That's what we get. And it's actually drawn right there. I didn't even see that. I forgot it was an example. So yeah, you get a square as a result of that thing. You can see what's made out of that as a result. Maybe I can erase the other stuff afterward, but that is the square. That is the square. Maybe I don't have to draw the initial plane each time. Maybe I can just show you what's going through when you cut the plane through. But that's the idea, right? If you can actually take a big blade and cut through and actually have portions of it there. All right, let's solve a real life problem. A machine at a sawmill cuts a 4x4 inch, that'd be this is 4x4 right here, 4 inch by 4 inch. 4 inch by 4 inch piece of wood lengthwise along its diagonal. So they're cutting this way diagonally. So out comes kind of two triangular prisms. As shown, find the perimeter and area of the cross section formed by the cut. So I imagine they're calling that, well, actually it's an example. So you have this plane. Right, here's the 4x4, just this little guy right there, alongside the red outlines and such. And then this plane, it's a little bit drawn bigger there, and it's cutting through. That red is the cross-section that the plane makes with it. So it's a rectangle. It's a rectangle, much longer than it is wide. And we'd have to figure out, 8.5 feet is the length. But the width you'd have to figure out by using this 4x4 basis here. 4x4 in a right triangle sense. That'll make this 4 root 2. Right, 4 squared plus 4, etc. So you get 4 root 2 as that length. So they said find the perimeter. It's 2 4 root 2s plus 2 8.5s. So 17 plus 8 root 2 gives you something. Oh, sorry. It wasn't 8. It was 8.5. Oh, that's in feet. That's right. 8.5 feet. 8.5 times 12 is something. 96. Is it 100? No. 102? I don't know what it is. Yeah, 102. Double that is 204. So 204 plus 8 root 2. I got to be very careful when it comes to units. They also said find the area, its length times width, 102 inches times 4 root 2 inches. And these are in terms of inches, right? So this is inches, this is square inches on this guy here. So they do some rounding. Awesome, awesome, awesome. Okay, overall, that is a relatively short lecture portion, but please, please, please rely on their artistry as much as possible, because if I have to draw some for myself, I think I'm going to be in a heap of trouble. Like I said, my perception is a part of your learning outcomes being excelled, being enhanced, and then your perception is also going to be very important as well, especially if they draw it, right? These are drawings here that they made. You have to understand this is a cylinder, this is 3D shaped, etc. We'll talk about it when we get to the problem itself. But me calling something what it is, you're going to have to see that perception for yourself as it's 3D superimposed onto a 2D image, onto a PDF, onto a piece of paper if you printed it out. Let's start with the vocabulary and core concept check, numbers 1 and 2. Number 1, complete the sentence. The intersection of a plane and a solid, well, that's called a cross section. Now, I've always abbreviated the phrase, and I might do this accidentally time and time again. Sorry, I said abbreviated. Hyphenated. I tend to hyphenate cross-section. I think it's supposed to be, but then the book doesn't do it, so I don't know. I might do it. I just did do it there, knowingly. Just giving you a heads up. Can a plane intersect a rectangular prism and form a cross-section that's a circle? Explain. No. If you imagine a rectangular prism, it has all rectangular faces. There is no such way that a plane can create curved edges out of this one cutting through it. Whether I cut through vertically and you get this cross section out, that's still just another rectangle, or horizontally, those drawings aren't too bad, but you get the cross section right there, still a rectangle. You can cut diagonally and you can still see like rectangle bits. Well, that cross-section ends up getting something else entirely. But it's never a circle, right? Never any curved edges can show up there. A lot of other shapes can show up, and we saw trapezoid as one of them. So no curved edges will ever exist from a rectangular prism cross-sections. There's my hyphenation again. Okay, guys, we are going to go ahead and get started to the official problem set, if you will. Numbers 3 through 26 will be popping up. This will either be long or short, all depending on what I need to describe and what I need to draw. We'll see how this thing goes. Let's go ahead and get started on this. Let's start with problem numbers 3 through 6. Describe the shape formed by the intersection of the plane and the solid. They're just saying give it a name. Remember, the purple is the cross-section, right? And keep in mind this has a three-dimensional, appearance to it, so just be very careful. I'm not going to redraw it. It's already there, so I'll just provide the answer from what you have. But a cylinder that's laid on its side and then cut vertically, if you will, that cross-section is a circle, right? Just like the circular bases that you have there on it. So that's a pretty quick question in and of itself. Number 4, you can see that this base here has all congruent sides and a right angle. A rhombus with a right angle is known as a square. This cross-section is horizontal and parallel to that base. This cross-section is also a square. This cross-section, too, is a square, just like its bases. And like the cylinder, those bases, this cross-section was parallel to those bases as well. Number 5, this is, unlike, we actually saw a cone that was cut horizontally and had the circular cross-section. This one's cut vertically through it from that top, from the apex downward. You can see it in this triangle here. It's a very specific triangle too. Because all slant heights are congruent in a right cone, this is an isosceles triangle, and I want to be specific about that. This is a triangle, yes, but it's an isosceles triangle because of the congruent aspects of these two right here being the same length in terms of that cone. And number 6, we have an octagonal prism. It does appear to be a regular octagon, but I can't go as a certainty there. But it's cut vertically through its laid down version of it. It's parallel to the bases. This is an octagon. Perhaps regular. Don't know. It's at least convex. There's your octagon. Okay. Good. 4 questions done really quickly. Numbers 7 through 10, draw, this time it's up to us, draw the cross-section formed by the described plane that intersects the red line segment drawn in the solid. What is the shape of the cross-section? Now, it's possible that because they, I'll even copy the text that they have there, because it's possible, because they already have the red line, it's possible that I might be able to do this without drawing the entire plane. I can probably just continue on the path of what's there and go from that. That might be very possible. Plane that's perpendicular to a base. So your base is this pentagon right here. The exiting shape won't necessarily be a pentagon. If I follow this red line, this will cut vertically now down through this edge, and it will come down through this edge as well, and it'll meet there. So I don't think I need to draw the full plane. I can just give you the idea of the cross-section right here, and that should have a 2-scale appearance to it, just looking like a rectangle. It is a rectangle. It's not slanted. Keep in mind, this is very upright with everything. The pentagon things on top and bottom is just going across this way. So it is a rectangle from this one. They said draw it. Did they say identify it? Draw the cross section. Yeah, what is the shape of the cross section? It's a rectangle. So I'm going to go with that on the drawing. I think I can just do that for these ones. That might make it go a little faster. Number 8, plane parallel to base. I have to copy and paste all these. They give you the red line, and we'll continue that path as we stay parallel to the base with said plane. So if it's parallel to the base, it is going to make the same shape as the base. Not congruent to it, but indeed similar to it in this case. So what is this, a pentagon? Yep. So my exit here will also be a pentagon. It's going to stay parallel to the base, and it's going to come along these edges here, right? If I did draw a plane, the plane that's actually going through it, it's just a horizontal plane, and I have no way of showing that to you in a good sense other than this is going horizontal through that thing, and there's the cut outline of it, right? That's why I'm saying none of my drawings are going to be really fantastic with it. But there is your pentagon. Pentagon. Hopefully this is going okay for you. I'm very much understanding what's there, but hopefully that you're getting that same sense of understanding either through my explanation, through my visuals, or you just get it. All right? Hopefully you can just get it. I feel for you if you have to make the drawings yourself. I don't really know how to address that. Thankfully, I get some copy paste maneuvers within my work. Number 9, plane parallel to the bottom face. So the bottom face, remember this is a triangular prism. This is not a pyramid. But that doesn't make this thing on the bottom a base. In fact, this is a base and this is a base. That's neither here nor there. The point, though, is that this cross-section is parallel to it. So when we run parallel, let's stay along the faces of what happens. We're going to come on this other side over here and through here and out here like that. I don't know if that maintains similarity. I have no reason to assume that it does. Wait, does it? I guess if it's parallel, then yeah. No, not similarity. The length is still the same as it was before. Anyway, it's still a rectangle. It's a less wide rectangle than this one is. Same length, right? Whatever this L is, this is still L. If this is some W, that ain't W. This is some X, right? It's some less than W there. Anyway, it's a rectangle. That's a rectangle. What is great about them, not great about these things, what's interesting about these things, as you've kind of seen, is you can cut this in different ways, even if it's the same shape. If you cut it in a different direction, you get a different cross-section. So I'm sure we're going to have to be dealing with that in a bit. Number 10, plane is perpendicular to bottom face. Now we're going to be cutting vertically through this, if you will. Hold on, I didn't get the whole thing copied there. Sometimes I get a little bit of my purple circle, whatever kind of color you call that. So perpendicular to the bottom face, this is, once again, it's a certain kind of prism. It's a trapezoidal prism, trapezoid on front and back. And this cross-section will, too, be a trapezoid, congruent to the other ones, assuming those two are congruent, and this is a prism. So right there, you get a cross-section. That's trapezoid. I think that's the early learning of how you're going to see some cross-sections to begin with. Then I think we have to draw them for ourselves without the lines. All right, ready to go? Let's keep going. I wonder if we have to do error and out. Here we go. Error analysis, number 11. How do they do it? Describe and correct the error in describing the shape formed by the intersection of the plane and the regular hexagonal prism. They called it a trapezoid. I see the want to do so, but because it's a hexagon, when we run down these sides, these faces here in green are two parallel to each other. They too are parallel to each other because it's a regular hexagon. And if they're parallel to each other, meeting across these opposite corners here, we'll keep these parallel as well. So these are parallel here, but these are also parallel here. So trapezoids don't have two sets of opposite sides that are parallel, just one. This would at least be a parallelogram. I see no reason why it wouldn't be a rectangle. I'd have to do some official kind of, work to try and get to that actual stating. How can I determine for sure that's a right angle? I just have to know. I mean, I know it's a rectangle. I have to kind of get the why of the matter. You know what I could do? Maybe I can't show those are the right angles, but I could state that these are congruent diagonals. That one's congruent to that one. Given the nature of a prism and being a regular hexagon, those would indeed be diagonal to each other. Rectangles would have that. Parallel, not all other parallelograms would. So, trapezoids don't have both pairs of opposite sides parallel. Yet this cross-section does. Because the diagonals are also congruent by nature of the hexagonal prism, this is a rectangle. Not necessarily just a parallelogram. It is a rectangle. Okay. All right, let's go on to number 12, open-ended. Give an example of a solid from which a triangular, hexagonal, and trapezoidal cross-section can be formed. Oh, we saw that from a cube. Oh, we didn't see hexagon. They didn't say regular hexagon, though. So can you do that from... I assume you can do it from some sort of rectangular prism or cube or something. Let's try it from a cube. I don't think... I've never tried to look, but I don't think this thing can draw cubes. So let me just form my own. Sorry. Now this is where we get to kind of play with this in several different ways, right? So we have this guy here. Decent enough looking cube with that. Let's get some dotted lines for the back ends. Okay. So we have, whoopsie. Good enough. We have ourselves our cube. The trapezoid, sorry, let's start with the triangle. The triangle begins with, you know, drawing a plane. I'll do it kind of, see, this is where I'm going to run into trouble. Drawing a plane that goes into the shape and out the other side in such a way that it's, oh, I'm going to have so much trouble with this, guys. I don't know how to manufacture the 3D-ness of this that you can tell. I'm going into the bottom corner and out the bottom. So I'm basically hitting this facing here and out the bottom like that. I don't know how to makeshift this for you guys to see the triangle. You saw a triangle earlier, right? I want to do this best so that you get it. Let's go through the top. Maybe I can get it from there. Okay, so this part here. This, and that. So that plane cutting through there gives me a triangle. Triangle one with the cube. So there's one. Okay. Let's do the trapezoid. I'm sorry, this isn't going to go too well. Let's do the trapezoid. Trapezoid is where I can... I don't want to make it a rectangle. How did they do trapezoid? I guess you can go through the diagonal again, but you have to go more in to, say, the bottom. So you have to slant this thing. I can't go vertically. I have to slant in such a way. It kind of needs to look like a trapezoid as if I'm going more into the shape, like that. So it's going in right there. Let's see if I can do this. The cross section is going in right there, and out this side it's bigger. It's bigger, say, on that side like that. So that would still be the trapezoid idea. It's not going too well. As far as my drawings go, it's not going too well. But that would be the trapezoid. Now a hexagon. Can I do a hexagon out of a cube? I have to enter and exit. So I have 6 facings. Maybe I could have done it with a hexagonal prism. Hexagonal prism can do the... Oh. Yeah, triangular, trapezoidal. Maybe I can use the hexagonal prism and do the same thing. I don't know if I can make a hexagon out of this. If I do any sort of cross sections. Here, if I cut within that corner. How about this? How about if I go through diagonally like that, but I enter and exit on these parts here. So I have to hit the back side. I have to like hit right here, but right there, and then downward and out the other side. Would that make a hexagon? I suppose. I just don't have a way of visualizing it for you, but I assume that a cube can do that if I can just exit out those sides like that. Not the best version of drawings. This is where I knew I would struggle. This is where I said we're going to have some issues here. So I assume a cube is possible if I have something like that done. Let's just go with the hexagonal prism that they kind of were talking about before. I think I can guarantee it there. So might have had a little time waste there, a little bit of time suck. Let's dig that one out just so I played with it. I tried it. I don't think it prospered in the way that I wanted to. Let's go to the hexagon shape by nature, like this, and let's try it that way. Did they ask me to draw them? Because I'll give a drawing, but I don't think I'm going to live on it for too long here. So here's a hexagonal prism. Sorry about this again. Okay. A triangle, I can go in and out of one of the corners. I think actually one of these corners would just be best on the side that we can look at. So I can do like right here, go in and out of this corner right here. The cross section would then kind of look like, I don't know, this won't be a perfect look, but you know, something like that, right? Triangle goes in and out like that. So there's one of them. Next one's a hexagon. Well, we can do a hexagon. We can just go parallel. So I think that's why I wanted to do it this way. It's going to be a lot easier to see it like that. Let's just go horizontally through this thing, in and out of it. Boom. Parallel to it. So going off the back side like that. And then what you're getting now is just this hexagon cross section, right? You know, whoa, wrong tool. Wrong tool. Right here, and then kind of dotted lines on the back end, which I probably should have done with the other shape there. So there's that guy, right? Then a trapezoid. You know, with the trapezoid, what you would kind of have is like, I just did it before, but you go in and out of some set of sides, but you got to go at an angle, not the same way as the triangle. But I'd have to do something like, if I go this way, I have to keep the facings sort of, hold on, I have to slant it. So maybe something like that. If I have to do this for every problem, guys, we're gonna run into trouble. So here would be something like, maybe it's lesser here than it is up there. So like this guy is longer than that guy is down there. You'd have to skew it in a certain way to make that happen, but that would give you the trapezoid one. So I'm just gonna call it hexagonal prism with that in mind. Okay, so did my best with it. I believe that's the nature of what we can do on it. But it needs to skew itself in such a way that it's lessening itself on that other side. Yeah, I don't know if I did that perfectly, but there you go. All right, tried my best. Number 13 through 18. Draw, here we go again, the cross section formed by a vertical plane that divides the solid into two congruent parts. Is there more than one way to use a vertical plane to divide the figure into two congruent parts? If so, does the cross section change? Explain. Okay, number 13. This is again a copy paste job here. They said draw it vertically. So if I do, they did say two congruent parts here. So this shape, if I draw the vertical plane, you know, this way, I'm not going to do this very long on these ones. If I do it this way, right, it's vertical, but if I do it this way where this is my cross section, right in the middle right there, it makes this part, the solid, congruent to that solid there, right? So that can be the drawing. That's one way that I can do this one. Another way that I can do this one and still make it two congruent parts is if I wonder if there's another way. But I can also draw the plane, you know, this way, dividing this part right down the middle. You know what I should do? I shouldn't draw the whole thing. I should just draw the actual cross-section portion I'd be doing, right? If the plane goes vertically like that, this would be my cross-section here, and that divides this part congruent with the other part, right? A third way that might work, let me try this, is hitting the corners. So what if I went corner to corner? It has rotational symmetry, but not, I don't know if this cross-section works though. So going through this plane, it actually goes kind of on this part here and back up. I assume those are congruent to each other, right? Just the cross section isn't any one distinct shape with the way that it curves in. It doesn't go down this curve right here because the plane needs to stay right there. So I think those are the three, really four different ways you can do it, because you can hit this corner as well on the other side, but that's just the idea, right? You can do one corner or the other corner. So I think there are four different ways. Let me do that fourth one. I think there are four different ways you can do it and still have it work out. That's just my best guess on that. So again, corner to corner here. And it goes straight down to this guy, but then cross-section wise, it has to go into this part right here and kind of back up into there. the way that it cuts through. So I assume there are 4 of them. Okay. Whoops, I didn't want to delete the actual cross-section itself, because I assume those ones are congruent on that one. All right, that is number 13. That is number 13. It's my best guess on that one. Number 14. They said with vertical, because these are vertical planes, right? I'm taking the vertical plane, I'm rotating it these different ways like that. It still is vertical. So number 14, I can only really see one way that I can think of that would maintain congruency for your 2 different objects, which is, I mean, they're all vertical, but cutting, let me draw it. Let me know if you see another. Cutting, you know, this way, right? This, where's blue? Cutting this way like that, right, would maintain congruency, and this would be the cross section of it. So this side is congruent to that side right there. There's no other vertical one I can see that would maintain congruency of the 2 objects. So I think that's the only one on number 14. They're not asking for the name and the shape, so that's all I'm going to do on that one. Number 15, as far as a vertical cross section goes, I can really only see one that I can imagine here. See, if I cut like through here, that doesn't make this part congruent to that part. The only way is if I kind of cut this way, right? Cut this way so that I'm literally looking at this aspect of this cross section right here. Just this triangle mixed with this rectangle. Remember, when I cut vertically this way, that ends up being a rectangle right there. So there's my cross section, and it divides the front with the back evenly. Even this part's a part of it, right? It's a part of the cross section bit as it's going flush through that entire thing. So hopefully that's making sense, and I think that's the one and only cut that you have. I don't really know how to explain. They say, does the cross section change? Yes, it does. Now my visuals hopefully show that this one here is a rectangle, this one here is like a semicircle, you know, and this is I don't know what that is. I don't know if that makes them congruent. I assume they are, but there's that. This one only has 1. This one only has 1 that I can see. Number 16. When it comes to vertical cuts, I think I have multiple options here. I might even have 4. I don't know how to do, you know, across those diagonals. That is probably possible for congruency's sake. So let me shrink this thing. Kind of copy, paste, get them all ready to go. So the bottom 2 I'll reserve for the end. But on the first ones, right, I can cut down the middle like this and get that appearance of cross section. So there's one of them. Second one, I can just cut down like this, right? Go down this other part, and yes, the shape changes there. So totally different shape change. This one's a, you know, different kind of object, and that one's more of a rectangle. I guess if I go across the corners, that same kind of weirdness can happen here, where I can get some congruency on both parts. So cutting across here, but it won't just go up the top like that. It'll go up the top in the middle and back down the other side. So it'll go across like this and then down the other side from the middle to that corner like that. So hopefully you can see that shape a little better than the previous one we had. Now this one right here, I can do the same thing corner to corner, and then I can go across the top middle and back out the other side. And I believe you're creating congruent parts there. Yeah, it appears so. So I'm going to go with that. Number 17 would also boast 4. Actually, 17, you know, okay, 13 and 16, how I said it has those ones from corners, I imagine there's actually an infinite number of ways you can actually do those, so long as you go to the opposite portion and you go through the center. So I believe some of these actually have an infinite number of them. 17, I thought more of it because of the circular nature of this thing, 18 especially. I don't know if that's what they intended on you seeing with them. I think with 18 they do. We'll get into 18 obviously. But on any of these ones here, when I thought circle, I started thinking, well, it can enter and exit out of any side and you still maintain congruency of this thing. Remember, the circle part, this is cut out from that portion, right? So I could go, okay, we could go from end to end let's, or I could go from middle part to middle part across the center, right? And then I do this right here. Now, this doesn't create a rectangle or a square or anything this time. This actually gets something a little bit different because the inside is cut out. The inside's cut out. You end up just getting two triangles, right? I actually have to draw the rest of this cross section. I need this to go down here and this to go up here. What you see actually, this part shouldn't even exist, really. This should kind of be like faded or dotted or something, right? That doesn't exist in it. This does in blue. That's the cross section officially, right in here. So this guy, boom, 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 and boom, 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 is the official cross section of that guy. Now, if I cut it that way, great. If I cut it this way, the shape won't change, okay, because it's a cone, with the cone having a circular basis there. This shape here is the same. This shape here is the same as the other one that you see there, right? Now, this would go into that part. I guess I'm not hitting the right parts visually with that because that should probably just go right into the lines. Let me kind of back it up into here. Pretend like that it's drawn better. Anyway, I think it's really their drawing that messes it up. Anyway, it's these two triangles right here as well. These should be the same as this thing. And by the way, keep in mind, we're still cutting this thing into two congruent parts, right? The figure itself is being cut symmetrically into two congruent parts. But I don't think it ends there. I mean, it definitely doesn't end there. You can go corner to corner as well, right? So I could go across this one corner here, cross section, and it goes across the bottom through that middle portion out this other side right here. And it actually hits this before it hits the cone portion, and then it goes down to the bottom and then back out to this part and draws that line. Different shape than you had before, a little bit wider, right? Different set. You can do the same thing on the other side here. Hopefully you're drawing that connection with what we're doing on them. Same thing over here. I'll do, I guess I'll still make it solid because I want it to be the official part of it. And I'm showing where the exit, not where the exit portion is, but the part of the circle that's open at the top is not included as a part of the actual cross section. So these two should be congruent as well. I mean, these should be the same looking shape if you do one or the other. But see, I don't think it ends there. I think you could do it from any set. Like I could go from, say, I'm not going to draw it in full, but I could go from like this part here to this part opposite. As long as it goes through the middle, right? It can go, I guess I am drawing it in full. But, you know, it can go like that, and it still maintains congruency of both parts and all that. It just gets closer within. So that's possible. I just don't want to draw them all. And that could have been possible as well for numbers 13 and I assume 16. It still creates congruent parts, and it still has those cross sections. But I'll leave it at that. These are, though, the same. And these are the same, is my understanding. Now, number 18 is especially going to be same-z's everywhere. Here's the thing. You could draw it from one place to another anywhere you'd wish, and you'll have the same kind of cross-section. You'll have the same kind of congruent parts. It won't change. So no matter what I do here, from front to back, from left to right, whatever it is, as long as, because here's the thing, we got to go through its center, right? We got to make these things congruent. So we got to go through center, 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 center. No matter what we do, everything will always be the same on this thing. Cross section, congruent figures, not going to change. It's all the same. So go vertically. Remember, we're cutting vertically. So go vertically through it like this. Trapezoid. Go vertically through it like this. Hopefully you can see the 3D-ness aspect of it. Still a trapezoid. No matter which way I do, all of these will always be the same. There's an infinite number of these as a for sure. Not just infinite as an infinite number of ways you can cut it, but no matter which way you cut it infinitely like that, they'll always be congruent. They'll always be the same cross-section, period. Point blank end of story. Even though it looks weird visually on that. All right, let's keep moving forward. Number 19. Okay, a little bit more word problem-esque. You cut the cake vertically to make two congruent parts. Find the perimeter and area of the cross-section formed by the cut. So I imagine they're saying you're cutting it like that, right, in half. Boom, boom, boom. Okay, so there's the cross-section of the two semi-cylinders now we have for the cake. It says find the perimeter and area of the cross-section. Well, that is a radius there. So for part A, perimeter is going to be, first of all, let's double, the 7 to get 14 to get the diameter. But we're going to double that once again because if this is 14 on top, that's 14 on bottom. So we have two 14s. These are both set in inches. 2 14s plus 2 4.25s, which is 28 plus 8.5, which is 36.5 inches. That's a big cross section of cake. Area is going just to be length times width. So we have just the 14 times the 4.25. And that's something. Let me, I don't have my calculator ready. Give me a second. I imagine this was going to be cross section only, no calculations. So let me get it up. I don't think you have to look at me doing that calculation, so I'll leave it to the side. All right, 14 times 4.25. 59.5 square inches of rectangular cross section. Keep in mind, this was a rectangle. So, right, we are doing a rectangular cross section. We get to do length times width on that guy. Part B, find the surface area of the cake that is not frosted before the cut. How does the unfrosted surface area change after the cut? Is the frosted, you guys have to help me. How does a cake get frosted? Is it everywhere? It says before the cut. Is it just the bottom? Guys, is the bottom frosted in a cake? Frosted cakes are more than good. I'm going to assume that the bottom is not frosted, right? It's just the every other coating. So if the bottom's not frosted, we're talking about just the area of the circle on the bottom. So not frosted before. I just need to do my pi r squared for that bottom layer. So pi times 7, that's our radius squared, which is 49 pi square inches, which is about, let's do that, 49 pi 153.93804. That looks exact, so I'm just going to write it all. 153.93804 square inches. That's before it's cut. How does the unfrosted surface area change after the cut? So if you cut and split it, now you still have that bottom area still completely unfrosted, and there's still all of it. Just because you separate it, it doesn't change that. But now you have two extra unfrosted surface area sections, the cross section of this rectangle on both facings of the cake, right? When I cut this cake open, I have two semi-cylinders like this. Here's one piece of cake, and here's the other piece of cake, right, split apart, but they both have that cross section there. So it's these parts right here that we need to also include. Unfrosted, unfrosted when split apart. So that is two extras. Not frosted. When I wrote not frosted before, I meant not frosted before the cut. So not frosted after cut takes your 49 pi, that doesn't change, that bottom, plus the area, two of these areas of that cross section, two 59.5s. So I'll let the calculator do all of that. That plus 2 times 59.5. So I still have the other calculation in there. So 272.93804. I put approximately equals. I think these are exactly equals. No, they have pi in it. Well, if they have pi in it, then I guess those weren't exact. I guess those were rounded. Oh, well. I just trusted the calculator. All right, 272.93804 square inches. That's all right if it's a lot of decimals. I don't know when to stop on that, so I'm just going to work off that. Looks pretty good. How does it change after the cut? Oh, well, that's what it is. How does it change? 272 minus 153, because it's the same number there that we have. What is that? 119 square inch difference. Because the decimals at the end are the same, I don't really have to write them. So that much difference on it. All right, part C. Can the cake be cut another way to make two congruent parts? If so, find the perimeter and area of the cross section formed by the cut. Yeah, you could do, they did vertically. You could do diagonally in some way, I'm sure. You could do horizontally, right? So I cut horizontally right here. I have a top half of the cake and a bottom half of the cake. I don't think they're talking about frosted versus not. They're just talking about perimeter and area of cross section. So you could cut horizontally. By horizontally, I do mean parallel to the circular bases of the cylinder of the cake. So if you cut horizontally, you have a circular cross section. We know that area, pi r squared, as 49 pi. So we're good on that one. Area is 49 pi square inches. I'll just leave it like that. Circumference, well, I'll round it again, but 153 point what? 94. I'll just say 94. 94 square inches. The circumference is 2 pi times the radius. So 14 pi inches, which is about, I've seen that number quite a bit in previous problems we've done in the past. 43.982, so 43.98 inches. This should be square inches. Square inches and inches like that. So that's one version. That's the easiest to work off of, right? We're not going to do anything more with like diagonal stuff. I think that'd be way too much to do. Okay, number 20. Parts ABC. A mason uses a concrete saw to cut the block along the indicated diagonal. Okay, we're talking cross section that goes corner to corner or edge to edge, like that, down the other corner right here and out that other side. That should be rectangle. Excuse me, a rectangular cross section. We're gonna have to do some Pythagorean theorem lengths here, I'm sure. Identify the solids formed by the cut. So they didn't talk about cross sections. They talked about solids. The solids formed by the cut, we now have two congruent triangular prisms. I don't know if if we're supposed to draw them or not, but we have two congruent triangular prisms. Hopefully you can see how they are made by that. It makes sense. There's a rectangular prism before. You cut it to triangular base faces and stuff like that on top and bottom. So that works. And they're both, I think they're both congruent to each other with that in mind. All right, part B. Find the perimeter and area of the cross section formed by the cut. Okay, this time, so this 215 is that prism height, if we're referring to triangular prism in that way. So this is 215 as well. This is in millimeters. So we have that length. What we need is this length right here, right? This, I'll call it X. And this is where we're going to use Pythagorean theorem based on this being 440. I should probably draw this on the other side. And this being 100. There we go. So that X, being the hypotenuse of this. So we get 100 squared plus 440 squared equals X squared. Okay. That's what we're dealing with here. So that's 10,000 plus, I don't know what that is. 440 squared. 193600. All right, plus 10,000. All right, so X squared. Let's hope that this has a clean square root. It does not. So square root of 451 something. So let's just leave it as this, 203600. I could do my whole, listen, I could cut out 100. I could probably divide this by 400, right? Hold on, let me square it again. Squared, divided by 400, and I got 509. 509, probably a prime number. I don't know. I'll say root 400 times root 509, which is 20 root 509 millimeters. Either that or that. I just don't want to round early. I'll be rounding ultimately when they ask me to do that. But here's the thing. We need area and perimeter. So perimeter is going to be two of those X's plus two of the, what's the other number? 2 15s. So let's work that out. Square root of 200 times 40 plus 2 times 215 is 430. All right, 18, so it's about this number here. I'm getting 18,478.82 millimeters. That's perimeter. I'm doubling those because it's a rectangle, right? Just rectangular nature. That's what we're going to be getting off that guy. I have to look into that, though, because did I do that square root right? 203,600. 2 of those times 2 of those. Let me make sure that that adds up the way that I wanted to, because that seems like it might be a little off. Hold on. Okay, hold on. I screwed up my own number. I was thinking that looks a little big. It just seems like a big number. Because this number, right, square root of that, I got 450 something. So there's no way it should be in the tens of thousands. I think I actually multiplied by 40 because I said 2 root 509, 20 root 509. So this should just be 2 times, let me do this again. 2 times square root of 203,600. Okay, that's it, because I did 40 before. Plus 430, 215s. All right, 1332.44. 1332.44 millimeters. Okay, these numbers are right. I just accidentally, I had 2 times 20 here, and instead of 509, I wrote 203,600. So now we're good. Okay, area is going to be base times height, length times width. So 20 root 509 times 215. Or 4,300 root 509. Square millimeters. That's an exact one. Let's try and figure that out now. 4,300 times root 509 gives us 97012.42189. So 97,012. Now, I trust this one because it's a multiplication of what's there. I was looking at the other one. I said, how did I get thousands? How did I get in the tens of thousands when this number was hundreds and this number was hundreds? And we're adding them together. That didn't make any sense whatsoever. Now it does. Okay. There's a perimeter area of cross-section. That is part B. Let's go to part C. Let's see if I have room for the bottom. The block has a density of about 0.002 grams per cubic millimeter. Find the mass of the block to the nearest gram. So we learned density is mass over volume. We can identify the volume of this by using length times width times height. This has nothing to do with cross-section, actually, by the way, guys. Our density is 0.002 grams per cubic millimeter. We do have millimeters that we're referring to here, so we can keep that going. Volume of this, again, is going to be length times width times height. Let's do 100, 440, and 215. And this will give us cubic millimeters of this thing. 100 times 440 times 215. And we get 946,000. 9 million? 9,460,000 cubic millimeters. So 0.002 equals mass over that. So we multiply both of those things together to solve for mass. So that times 0.002, I think that's divided by 5,000, divided by 500, 5,000, 5,000. And you get 18920. Mass is 18,920 grams of blockage, right? That's what they want, to the nearest gram. That's just the whole number. 18,920 grams of concrete block. I'm digging it. Okay. All right, let's go forward to number 21. Still 6 problems to go. Use the figure shown. One of the hexagonal pipes is cut vertically so that it's divided into 2 congruent parts. Okay, they're basically sticking. I think I understand the picture. I don't know if you do. I think it's just 3D. I don't know. But okay, so one of the pipes. Okay, they're pipes. They're cut. I just don't understand the square on the outside, I guess, is the picture frame. Draw 2 possible cross sections as if this pipe was cut vertically. Okay, so this pipe, so you don't see the entire pipe in and of itself. I thought it was already cut. So on part A, let's do, I'm trying to make a 6-sided shape here. I'll just copy and paste my own drawing after this. I'll make it a hexagonal pipe like so. Let's do this. Hold on. I want to copy and paste this guy, but I want to use dotted lines for this one, and I'll fill in those solids like I kind of just did there. Let's see if this will work. I mean, it's going to work. Let's see if I can make it look good. Whoa. Yeah, half of what I do is in my artistry, right? Hopefully you're like, man, that looks cool. There's that. Now let's do a couple dotted lines here. Probably should have done this for some of the earlier ones. All right. You know. Yeah, not bad. Okay, so there's this guy, right? Now, let me make two of these. There's one, there's a second one. We got to cut it two different ways to make what? It's cut vertically, so it's divided into two congruent parts. Okay, so it's kind of like the stuff from before. So you can either cut vertically down the middle this way, so you make another hexagon. Okay, like that. And this part's congruent to that part. Or cut down the middle here. Remember, it has to be vertical. So you make just a rectangle. Right? A rectangle cuts out from this thing like that if you cut it that way. So there's one, there's the other. Hopefully that kind of makes sense, the two different ways you can go vertically on that thing. All right, there's part A. Part B. How many different ways can a pipe be cut lengthwise to form two congruent parts? What do they mean lengthwise? Ooh, I don't know what they mean lengthwise. Do they just mean the long? If it's the same thing as what we were doing before, like keep in mind what I was doing before with these questions right here, right? I was like, I can do any which way. I can do from the corners. I can do whatever here as long, especially this one. This can be infinite. I think that's just that answer, right? You can do it infinitely many ways as long as you go through its center. So I don't know what they mean by lengthwise, but if I go from like this end to this end like that, I'll still get two congruent parts no matter what. So let me paste this in and kind of like give you that idea, right? I can either go, I'll kind of make it big, bold, and green, if you will. I can either make it like this, right? From corner to corner like that. As long as I go through the center, I'll have two congruent parts. Boom, there's one. Or I can go across these ones here like that. And then boom, I have two congruent parts like that as well. So actually that looks really trippy. Yeah, I think you have infinitely many ways you can do that one. Infinitely many ways, as long as you maintain symmetry. I'll say rotational symmetry in your cuts, and it goes through the center of the hexagonal pipe. I think that's just the idea, because that's what we kind of saw in previous problems, at least to me. All right, let's go to number 22. How long have we gone? I was actually very curious about that. Oh, less than an hour so far. I think the lecture was nice, a little shorter. A regular octagonal pyramid is intersected by a plane perpendicular to its base. The plane passes through its vertex, so it's divided into two congruent parts. Draw the cross section. Is there more than one way to divide the pyramid? If so, yeah. Okay, let's do that. Octagon. Okay, I'm going to, it's a pyramid, so I'm going to have to do a little bit of that. I wonder if I can rotate it and still make it, I can't skew it. So this is just going to have to be how it is. You're going to have to deal with it. So I got this guy here. I'm going to draw a center, if you will, and an apex above it. And we're going to go to work. So I got, this actually won't look too bad because you can see all points that it still hits. What I do probably want, though, is the pyramid to be, the base to have dotted line things. Give me a second here. And I'll fill in the solids that we should be able to still see. There we go. That actually looks kind of cool. Happy accident there. I still need to draw the back things here. I don't know if I need them all. I might, because I got to play with cross sections. So I just got to prep my drawing. And I could probably do this a lot faster on paper or on a whiteboard or something, but because we're doing it that way. Okay, that looks good enough for me. So I have an octagonal pyramid. It's intersected by a plane perpendicular to its base. So anything that I do that's vertically upright, like that, one of those ones. The plane passes through its vertex, so it's divided into two congruent parts. Draw the cross section. So we can do, I'll go straight up. I'll actually just make a rectangular shape right now. Let's see if I can do this. Fill color, line color. Did I make a rectangle? I did. And let's make it kind of transparent. Oh, that didn't work. Oh, that did work. Okay. So if I did a cross section like through the middle like that. If I did a cross section kind of through the middle like that, then, you're creating this triangle that was the plane. The triangle's the cross section that it makes out of it, right? If I go perpendicular to the base like that. Is there more than one way to divide the pyramid into two congruent parts? If so, does the shape of the cross section change? So this is one way to do it. In any other way, that it goes through, say, the middle of any two of the edges. So that one, or from that, from this to this, or if I went, in red from this to this, or in yellow from this to this, all of those perpendicularly going through that apex would create the same exact cross section. It would be the same two congruent parts. It would be the same thing, just cut in a different slot. Assuming this is a regular, is it regular? Yes, a regular octagonal pyramid. So those would all be the same. But if I had this more on its diagonal cut, so that I go through the cross sections where it hits an edge, it still would create triangles. It would just be a different version of it. So what if instead the cross section was here, through that center and out the other side right here, like that, boom. It still creates a triangle. It's just a bigger triangle. It's still an isosceles triangle as well. It's just a bigger one. So there are two different ways. You can create isosceles unique. There are two unique isosceles triangle cross sections. That can be formed either by intersecting with a slant height, with two slant heights, or intersecting with two edges. So that's kind of it. There was one, and I did another before. Let me draw it again. I'll do it in green. So one is the slant heights, one is the edges. The green is the slant heights. The blue is down the edges, like that. And I did one, yeah. So I think those are the only two, really, that you can do with it. I mean, there are others, right? I can do it along other sorts of the form, right? There's an infinite number of ways, technically, but I think those are the ones that you want to really work off of. So yeah, I guess there's an infinite number if you really think about it, but yeah, just go with it. It's always going to be a triangle, though. It's always going to be isosceles triangles. It will not change the shape, just change its size. All right, number 23. Making an argument. Your friend says any plane that intersects a sphere forms a circular cross section. Is your friend correct? Explain. Not always a circle, but it would always do ones with edges, unless they can consider one that intersects at just a single point. I don't think that they're ever counting those ones, and I don't know how to draw a sphere. So let me try. But I guess argumentatively, yes, you can. If you intersect at a single point, then that is different, and if you're intersecting, that does count. So let's do something like this. Actually, that doesn't look too bad. All right, so there's a sphere, right? No matter where I do some sort of plane intersecting with these things, it'll go in and out of this circle, of the sphere, I should say. It'll go in and out of it in such a way that it would always make a circle. So if I did it in and out right there, then boom, make some sort of circular cross section. I don't know if it's literally a circle versus an ellipse. I guess it would always still be a circle, I suppose, I think. Even if it was, it's still circular in nature. But what if I just touch it tangentially? What if it's just on the bottom? Just on the bottom, and then, boom, it hits a point right there. That's its intersection. That's not a circle anymore. So it can intersect at a point. My friend is not correct. I'm just trying to find one counterexample. It can intersect tangentially at a point. And that's all I need. Is your friend always correct is the question. I guess the answer is no, not always. Okay, number 24. How do you see it? Draw a plane that intersects the cube to form the given cross section. Oh, look at that. Hexagon is possible. So maybe number 12, I think it was number 12 that was open-ended. Maybe I could have done a hexagon. And look, they made a cube for us. Oh, golly gee, maybe I should have actually used theirs before. So I'm copying and pasting theirs. It's going to have this background, but that's okay. I got to do it 6 times, so let me just like make all these. Listen, I'm not going to draw the plane that surrounds it because I'm not going to make it look right. You want to understand the visual with it. I don't think that was helping earlier, so I'm not going to do it now. I'll just do the cross section itself. So an isosceles triangle. An isosceles triangle is if I cut it in such a way that it goes through one of the edges, kind of like that, and it hits these points identically there and out the other side like that. That would be an example of my isosceles triangle cross section. But, as I'm stating right now, this would go diagonally into it on this corner and out the bottom edge like that. That would be part A, if you will. I should probably write these out. A, isosceles triangle. B, equilateral triangle. More of the same. In fact, I might have just made one. Let me make this one be more so B, and then I'll make A be starting from something taller, like maybe from the top corner, like that. Start it from the top and then boom, it goes like that. So that one's more so isosceles, not maybe necessarily equilateral. B, make sure that it's equilateral by doing something. Oh, you know how you can guarantee equilateral actually? Go from corner to corner, because this would be, because it's a square or because it's a cube, this is the same length as this is and as that is. So this would be an equilateral triangle there, at least as a guarantee. These are all lengths of, like, if this is x and x, these are all x root 2s. This is just some sort of other form of a guarantee. I don't know how you can guarantee that's isosceles, but just make sure that these 2 points, these are the same distances away like that. C, scalene triangle. I don't know. It just kind of goes however. You still need to enter in like one edge and exit out another side. Like say I exited deep off this side and shallow off this side here on the cube and I started from there. Ooh, that might look isosceles still. Make sure it's kind of hitting in different spots, like maybe like that. Now it's probably scalene in nature. Let me use my cursor, not my mouse. So that would be more so scalene. Could be a right triangle, doesn't make it not scalene if so. Part D, parallelogram. Just make sure. Well, a rectangle is also a parallelogram, but make sure that you go in and out of faces. Let's see. I want to make it not a rectangle, though. Can I? I don't know. A rectangle is still a parallelogram. I just don't want to do one. Well, there are a bunch of ways you could do it, right? I can go through this part and out through this part like that and just make sure that it hits. So boom and boom. It still would be a parallelogram, I mean, all told. But it is a rectangle. It's also a rectangle, so I don't know. It still works. It doesn't not answer it. E, a pentagon. Now that's interesting. For a pentagon, you hit 5 sides. Could it go... What if it goes here? What if it goes down through this guy here and that side, 1, 2, and it hits these walls here and it hits the bottom? That would be a pentagon. So like that. So I was close because I tried to do hexagon in this kind of way. All right, so that works for pentagon, right? It goes through there. I think my trouble with drawing as a hexagon before was trying to draw the initial plane. Right now I'm just drawing cross sections. So hexagon I do believe would work if it kind of goes across this top and does that same thing. So it goes across this top, slides across this corner here, and then that corner, therefore, it goes across the bottom but doesn't exit. So I could have done cube. I could have used a cube to create a hexagon with that nature, and I think this is among the ones that I could have done. So there it is. Again, I'm not really drawing the plane with it, but hey, there's the plane that goes through it. There's the cross section. I don't know if that helps you or hurts you with it, but there it is. Okay, I think that worked out. Parallelogram is just one that I'm kind of iffy on because I also made a rectangle, so not uniquely parallelogram. But I think that's okay. I didn't want to make a trapezoid. All right, 2 more questions. Number 25. A plane intersects a sphere 7 meters. Oh, I have to draw another sphere. Let me copy. Hold on. Let me copy my old sphere I just drew. That's a decent looking sphere. I don't know if I like the back side of my own cross section, but all right. Let's fix the back. Then we'll read the question. Okay. A plane intersects a sphere 7. Oh, I need a center. 7 meters from the center of the sphere. The radius of the sphere is 25 meters. Draw a diagram to represent this situation. All right, well, I started my drawing. Let's do the plane on the bottom like I was doing before. I'll actually just draw a parallelogram thingy. So, like that. It's a little fat. Probably do the same thing, make dotted line bits on it. So, thin it out, dot it out, and then solidify it. Right here. Sorry, I like to have more fun with my drawings than you even know. All right, so this plane, it's intersecting, let's say, because I need to make the cross section that forms it, right? So here's the cross section that the plane forms. So that way it's, you know, it's a part of the sphere's bit, because we need the center to be 7 meters away from the cross section. So let's say like that, right? This here is 7 meters. But then they said that the radius is 25 meters. Now the best way to go about this is to draw a radius, right? Well, to draw it to the cross section. So this would be 25 meters like that. So then we make art. The shortest distance to any cross-sectional thing, by the way, to any plane, will be perpendicular to it. So this would make a right triangle. I think that's the important aspect of it that will bring about. Draw a diagram to represent, find the area of the cross-section to the nearest tenth. So the way to find the area of the cross-section is finding the cross-section, the circle's radius. So this circle's radius here, we'll call it x. This is part of a Pythagorean triple. 7 squared plus x squared equals 25 squared. You do the grunt end of the work, you're going to get 24. Grunt end. Brunt end? Is that the word? 49 plus x squared equals 225. X squared equals not 225, 625. 625. X squared equals 576. So x is 24 meters. So x is 24 meters. That's our radius of our cross section of that thing, that circle right there. So the area is going to be pi times 24 squared. We just saw that as 576. So that's an exact answer. It's approximate answer, rounded to the nearest something. 576 times pi, 1809.56, 557, 1809.56 square meters. And that should be your area of your cross section. Okay, there's that one. Let's finish off with number 26, thought-provoking. Describe a solid that can be intersected by a plane to form the cross-section shown. Explain how you form the cross-section. Well, that's not completely circular, so I can't call it a semi-cylinder. You could do a lot of different things with that, depending on it. I mean, there are two that come to mind. One is kind of a cylinder. You know, think of like an airplane hangar. So I have like a airplane hangar like that, and it kind of just exits out like that. So my cross section would be, you know, cutting like right through this part right there. So there's one version of it. It's not exactly semi-cylinder, but there's one area. I mean, that's a vertical cut. Vertical cut. Another version, and I guess it would still be a vertical cut, and I'm trying to think if there are other ones that are just as easy to make, was doing the same version of that kind of shape thing, but kind of making it a little more like, it's like half an egg, and not the way that you probably think with it. Like imagine that you have an egg, you know, it's kind of whatever, and you, oh, but it's half an egg, right? So this egg is cut in half, you know, right there. Not this cross section, just this is a portion of the egg. I'm going to erase the bottom part. But there's that part of the egg, and then here's the other part of the egg right there. So there's no bottom half of the egg. And I still cut vertically through this one as well. So it is half an egg, but then I'm getting this cross section there. It still kind of gets that appearance of a vertical cut. Can't really think of what else I want to do with it. I mean, those are the thoughts that I have with it. I'm trying to be a little more inventive with it though, because those aren't actual like like geometric shapes, like because it's not an actual cylinder and stuff. How about this one? What if, because I'm thinking conic sections now, literally. I don't know if you know what a conic section is, but they are the ways that you can cut into a cone. And I'm thinking of the hyperbola and kind of the parabola. But if I have a cone and I cut vertically down through it, but not through the apex, but I cut vertically down straight like this, for example, like that, it's going to cross through this part, and it's going to have to curve to go in and out of that part right there. I'd imagine that to be that same cross section. So vertically cut as well through a cone. So that's probably the best one that they'd probably be looking for, because I'm looking at that and saying it's not a cylinder, not a semi-cylinder, but it looks like a conic section, and I believe that's something you could do there. Vertically cut and make sure it just goes out the bottom like so. All right, guys, that's my best open-ended version of it, and that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. I don't know if it worked perfectly. I know there were 2 questions that I kind of struggled with when it came to the visual and what I wanted to do with it, but I hope that we did the best that we could, and I hope that you perceived it as best as you could. So, guys, thank you. Take care. I will see you in the next one.